Let's think about a physical car for a second. Yours, mine, doesn't matter. It has specific data, right? Like its current speed, its color, and exactly how much fuel is left in the tank. But it also has behaviors. It can accelerate, it can brake, it can turn. Now, notice how the real physical world doesn't separate the abstract concept of speed from the physical act of braking. No, it bundles all that data and all that behavior together into one single cohesive thing, the car itself.
Well, believe it or not, that exact bundling idea, keeping data and behavior completely locked together as a single unit, rather than just leaving them scattered all over the place, that is the foundational concept behind how most modern software is actually built. Instead of writing these endlessly long procedural lists of instructions where the data is just sort of floating around independently from the functions that modify it, we package them together. We're literally creating software units that mirror the integrity of real-world items. And let me tell you, this approach fundamentally changes how we organize, scale, and maintain massive, complex systems. So, right at the heart of this whole approach are two huge concepts you absolutely need to know: classes and objects. And the difference between them? It's crucial. Basically, a class is a structural blueprint, or a template. It doesn't actually exist as a physical item yet. It just defines the structure, like the name, the ID number, and the behaviors a student could have. Objects, on the other hand, like Jenna, John, Maria, James, those are specific, unique instances built directly from that blueprint. To go back to our car analogy for a second, the class is the engineering schematic sitting back at the factory. The object, that's the actual physical car you drive off the lot. You literally cannot instantiate an object without a class to serve as its template. Now, the core principles that make all of this actually work are often called the 4 pillars. Let's dive right into the first one, encapsulation. Think of encapsulation as this protective shell closing completely around an object's internal data. I mean, think about it. Would you want just anyone reaching in and randomly changing your car's fuel gauge from full to empty without actually burning any gas? No way. Encapsulation prevents exactly that. It bundles the data and the methods into a single unit and strictly controls access using public, private, and protected levels. That private data, it's locked safely inside the object, totally hidden from the rest of the program. If outside code wants to interact with that data, it has to use the public methods provided by the object, like knocking on a carefully guarded door. This is absolutely crucial for ensuring data integrity and keeping our code organized. Okay, so once that data is safely protected, we rely on the second pillar, abstraction. Abstraction is all about hiding insanely complex implementation details behind a very simple, predictable interface. So, when you sit in the driver's seat and push that start engine button, a massive, explosive chain reaction of electrical and mechanical engineering happens. Fuel injectors fire, spark plugs ignite, pistons pump, it's the whole shebang. But as the driver, you don't need to know how any of that works internally. You just push a button. That is abstraction in action. And in software, we do the exact same thing. We create these incredibly complex mechanisms, but we fold them neatly away behind a simple, clean interface. Other programmers can use our object without ever having to understand the complicated logic hidden inside it. It's a real game changer for simplifying complex systems. Building right on top of that simplicity is our third pillar, inheritance. This is what allows us to avoid writing the exact same code over and over again. Just imagine a family tree structure. Let's say we have a general, basic car class. It has standard properties like wheels and doors, and behaviors like driving and stopping. But what if we want to build a brand new electric car? Well, instead of starting entirely from scratch and rewriting all that code for wheels and doors, our new electric car subclass simply inherits all of that from the car's superclass. It gets all those existing features automatically. Then it specializes. It adds its own unique behaviors, like charging the battery, or it overrides the engine logic to use an electric motor instead of gas. Inheritance promotes just massive code reuse and lets us organize our software into these really logical, hierarchical categories. And that brings us to the fourth and final pillar, polymorphism. It literally translates to many forms, and honestly, it is perhaps the absolute most powerful feature of this whole paradigm. Polymorphism is the ability of different objects to respond to the exact same action or command, but in their own distinct, specific ways. Imagine we have a whole fleet of different vehicle objects, a sports car, a huge diesel truck, and a hybrid electric car. If our program issues a single universal command to start engine, we don't have to write this massive clunky checklist checking what kind of car it is first. Nope, because of polymorphism, we just issue the command once. The sports car roars to life, the diesel truck rumbles, and the hybrid silently engages its battery. Each object intrinsically knows its own type and executes that command perfectly. Now, objects rarely work entirely alone, right? They interact through different relationship strengths. First up, we have association and aggregation. These basically represent a whole-part relationship where things are relatively loosely connected. Take a car and its wheels. The wheels are definitely part of the car, but they have their own independent existence. You can take a wheel off, and guess what? It's still a wheel. That's aggregation. But contrast that with composition. Composition is a much stronger, tightly bound relationship where the parts absolutely cannot exist without the whole. Think of a computer and its central processing unit, the CPU. In a strict composition model, if the whole computer is scrapped, the internal CPU goes right along with it. The parts have a strictly dependent existence.
So those relationships perfectly set the stage for two really critical measures of software quality: coupling and cohesion. Picture a totally tangled mess of electrical wires. That represents high coupling. Coupling is basically the degree of interdependence between different software modules. If modules are highly coupled, they are heavily reliant on each other. So pulling on one wire threatens to yank out and break literally everything else. We definitely want to avoid this. On the flip side, imagine one clean, self-contained, highly focused box. That represents high cohesion. Cohesion measures how focused a single class is on doing just one specific, well-defined job. The golden rule: we want high cohesion and low coupling, for sure. It makes our software infinitely easier to test, update, and scale over time.
So what does this all mean for you? Why does all this theory actually matter? Because these object-oriented ideas are, quite literally, the backbone of modern software. The vast majority of the world's largest, most robust systems are built using these exact principles. Major programming languages, we're talking Java, C++, Python, C#, they are fundamentally designed around objects. So whether you are opening an everyday mobile app to quickly check the weather, playing a visually stunning video game powered by a massive engine, or interacting with a global banking system, you are interacting with code organized into classes and objects. They are out there collaborating, inheriting, and encapsulating data millions of times a second.
Of course, with any massive technological standard, a few myths pop up that we need to debunk right now. First is the idea that object-oriented programming is the only good way to write code. Actually, that's just flat out false. Different paradigms, like functional programming, are actually way better suited for certain specific problems, especially when you need highly predictable, immutable data. Second, there's this weird belief that you absolutely must use all 4 pillars in every single class you ever write. Look, they aren't a mandatory checklist. They're guiding principles. You use inheritance or polymorphism when the problem actually calls for it, not just to tick a box. And finally, a super common mix-up. Aggregation and composition are not the same thing. Remember, aggregation allows the parts to exist totally independently, while composition is a strict dependency where the part dies with the whole. What we've explored today is a high-level landscape view of a massive, powerful paradigm. We've seen how bundling data and behavior into objects allows us to model our software directly after the real world. But this overview is just preparing you for a much deeper understanding. Each of those 4 pillars, encapsulation, abstraction, inheritance, and polymorphism, has incredible depth, and each one is going to get its own full, dedicated explainer. Thank you for watching the Tech Canvas. Complex ideas, clear pictures. Follow for more.